Assalaamualaikum warahmatullahi ta'ala wabarakatuh. My name is Atifah Zohra binti Raimi and my metric number is 1190926. So today my group would like to present our presentation titled Vibrometry, which is specialized in laser vibrometry. So here is our group members, which we have 4 members, which is me, Atifah Zohra, and next is Ainajdah binti Cik Hussein 1190920, Aina Biha binti Muhammad Rihan 1190946, and Nur Atila Syahida binti Syaifuddin 1190959. So for today's presentation, there are 6 main contents that we would like to present, which we will start with the background, and the second one is theory or working principle, and next is development of interferometric techniques, current issues or applications, conclusion, and the last one is we will state the references that we use in completing our presentation today. So the main question here is, what is laser vibrometer? So laser vibrometer is a remote measurement technique in the sense that it can measure accurately from 1 to 2.5% of RMS of reading at a distance greater than 30 meters, even if it is placed far from the measurement. This trait, which is not shared by the other non-contact sensors, such as those that employ fiber optic proximities, appears to be highly helpful in extending the range of applications for vibration analysis to include assessing huge civil construction. It is also has proven that it is to provide considerable advantages over conventional accelerometers in a number of instances, enabling one to attain outcomes that were unthinkable just 10 years ago. One may make precise and adaptable non-intrusive measurements by using a laser vibrometer as a simple single-point transducer. Errors from accelerometers, mass loading, which appear significant for estimating modal parameters, will not alter the results, especially when testing the light or tiny structures or strongly damped non-linear materials such as rubber. And in addition to the many situations where laser vibrometer has been used just to replace the conventional accelerometers, the intriguing findings have also been made in the area of advanced study. For example, it is including the measuring vibrations in tracking mode on moving or rotating objects and continuously scanning to identify mode forms along the scan lines. So these innovations provide practical answers to a wide range of issues in a variety of application areas, including the study of mechanism under operating settings, damage detection, material characterization, as well as several biological sectors. Moving on to the next slide. So the first laser vibrometer has been released was in 1980s, but due to their poor signal to noise ratio, or can be short form as SNR, and limited sensitivity, measurements could only be made on extremely diffusive surfaces or by covering the measurements with retro diffusive tape. However, only in the early 1990s did hardware and software advancements improve the performance and application of instruments, leading many researchers to begin using the laser vibrometry.
So next, I will continue with the working principle of laser vibrometry. As its own name says, this type of vibrometer uses the Doppler effect to remotely acquire vibration velocities. If a wave is reflected by a moving object and detected by an instrument, as in this case by the laser Doppler vibrometry, the measured frequency shift of the wave can be described as Fd equal to 2 times v over lambda, where v is the object's velocity and lambda is the wavelength of the emitted wave. To be able to conversely determine the velocity of an object, the Doppler or the frequency shift has to be measured at a known wavelength. This is done in the laser Doppler vibrometry by using a laser interferometer. So this above image shows the Doppler effect as the frequency shift of backscattered light. Okay, next, A scheme of a vibrometer incorporating a laser interferometer is presented in the above figure. The light from the laser is split into a reference beam and also an object or measurement beam by a beam splitter 1. The object beam passes through beam splitter 2 and is focused to a point on the vibrating object by the lens. The backscattered light is then diverted by the beam splitter 2 towards the beam splitter 3. At beam splitter 3, the backscattered from the object mixes together or interferes with the frequency shifted reference beam. The mixing process causes any frequency difference that will then create a modulated detector output signal. This reveals the Doppler shift in frequency. And lastly, the signal will be processed and analyzed in order to provide the vibrational velocity and displacement to the object or to the sample.
Okay, I will continue for the next part. My name is Naatila Shahida binti Shaipuddin with metric number 1190959, and I will explain about the development of interferometry technique, which is interferometry technique applied in laser Doppler vibrometer. First of all, what is interferometry? Interferometry is a measurement method using the interference phenomenon of wave, which is most commonly seen with light, radio or sound wave. Usually for interferometry technique, one light beam will be split into two light beams by beam splitter, and then when the two light beams are superposed, an interference pattern is formed, and then this pattern is analyzed by the detector to determine wave characteristic, material properties or the displacement of one of the mirrors, which is for this part, it depends on type of measurement that we want to handle. But what is the relation of interferometry techniques with laser Doppler vibrometer? For laser Doppler vibrometer, or known as heterodyne laser interferometry, is an optical method for the non-contact measurement of vibrations. Of course, when we talk about non-contact measurement, it has more advantages compared to contact measurements. Non-contact interferometric vibration measuring techniques provide a great alternative to the limitations caused by the contact measurements. For laser Doppler vibrometer, a laser vibrometer based on a small Mach-Zehnder interferometer and an acousto-optical modulator, which is Bragg cell, is used for the setup, as we can see from the figure. And this type of vibrometer records velocity with a greater signal to noise ratio at high frequencies. Okay, next is a basic schematic diagram for the Mach-Zehnder interferometer. Basically, for the Mach-Zehnder interferometer setup, there are three types, which is open path, fiber-based, and also planar waveguide-based interferometers. But for the laser Doppler vibrometer, they use open path Mach-Zehnder interferometer. In Mach-Zehnder interferometers, a coherent and collimated light beam is split into two, which is one as a reference arm and the other one as a sensing arm. And then these two light beams are then recombined to obtain an interference signal. We can see from the arrangement, when the laser beam crosses the Bragg cell and splits into two beams, which is 0 and the first order ones, the first of the beams fall on the measured object after passing the beam splitter, and then the light is reflected back from the beam splitter and reach a photodetector. For the second light beams, which is the Bragg order beams, after reflection in mirror passes through the beam splitter and then it will interfere with the first beam on the photodetector, and then the FM modulated signal on the Bragg shift frequency, which is VB, is received as a result of heterodyning. Okay, that is basically for the working principle of interferometry technique in laser Doppler vibrometer.
Assalamualaikum warahmatullahi wabarakatuh. My name is Aina Biha binti Muhammad Rihan, metric number 1190946, and I will explain about the application of laser Doppler vibrometer. One of the latest applications of laser Doppler vibrometer is to validate the optical flow tracking algorithm for breast cancer detection. Currently, the technology used for breast cancer is digital image elastotomography, or known as DIET. This is because DIET is a non-invasive, pain-free screening technique compared to MRI scan or mammography. It analyzes local tissue stiffness based on elastographic reconstruction or captures steady-state surface motion in response to low-amplitude sinusoidal mechanical actuation applied to the breast, identify region of high underlying stiffness, and leveraging the high contrast between healthy and cancerous tissues. DIET also uses optical flow algorithm to track points on a breast cancer. Yet, there is a limitation where this method never explicitly quantified. Hence, Laser Doppler Vibrometer is used to overcome this limitation. Laser Doppler Vibrometer can measure vibration from a distance without contact. Laser measurement is considered the most promising three-dimensional measurement method due to its high resolution, non-destructive, non-contact modality. Laser Doppler Vibrometer is used just to validate the horizontal arc of plane measurement calculated using optical flow for a series of breast-shaped phantoms. The following figure shows the experimental setup of this experiment. The Laser Doppler Vibrometer system consists of a controller and a sensor head. The vibrometer controller delivers signals and power to the sensor head and processes the vibration signals. Then these signals are electronically converted by decoders within the vibrometer controller in order to obtain the displacement. The light source is a helium neon laser, typically a low power class 2 visible laser. The class 2 laser used in this experiment is considered safe as the blink response of the human eye is typically considered sufficient to avoid eye damage. However, eyes were still protected with safety glasses for this experiment. Steady-state mechanical sinusoidal input oscillation of 16 Hz, 24 Hz, 32 Hz, and 40 Hz of low amplitude, 1 mm peak to peak is applied to the phantom tip. Horizontal out-of-plane displacement of the phantom surface were measured using Laser Doppler Vibrometer. The experiments were carried out on top of vibration isolation table in order to avoid unnecessary surrounding vibration. In this experiment, each phantom was equally divided into 4 sections and 9 surface points were recorded on each section. The figure shows the top view of phantom, and it is a summary of marked surface points on the breast-shaped healthy with a 20 mm and 10 mm inclusions phantom for displacement measurement. Meanwhile, the graph amplitude versus time is the data collected by Laser Doppler Vibrometer for a section of a healthy phantom. This data will be compared with the data taken from DIET for validation purpose.
Since more than 30 years ago, the laser vibrometer accomplishment in delivering measurements solutions for difficult applications have fostered an instrumentation culture of innovation unmatched by other vibration measuring methods. So these triumphs haven't satisfied the user community. Instead, they have stoked seemingly endless inspiration. The development of an instrument with a high power infrared fiber laser used in conjunction with a green laser for sighting purpose has allowed for long range measurements without sacrificing the signal quality. And after more than 50 years of innovation of laser vibrometry, the infrared laser technology is now integrating into the instrument designs for short range applications on optically uncooperative surfaces, eventually threatening the dominance of helium neon laser. So, in conclusion, the laser vibrometry significantly extends the measurement capabilities with respect to the traditional vibration sensors such as accelerometer and strain gauges. And lastly, This is the references list that we use as our reference in completing our presentation today. That's all from us. Thank you.